Hello, my dear students. Welcome you all to Sri Jayendra Rank Zone classes. I am your mentor and your friend for the subject chemistry, and I will be taking the organic chemistry. As we have started, my dear students, the general organic chemistry, we discussed resonance in the last class. Okay. Today we are going to discuss the stability of carbanions and free radicals explained by the concept of resonance. But before that, I would like you to remember some common stability orders, some common questions on the order of stability for different carbocations. Okay. Very first is resonance stabilization of methoxymethyl cation is more than 1 degree carbocation. Although methoxymethyl cation is also 1 degree, but it is more than stability is more than the primary carbocation C. So here the lone pair is in conjugation with the positive charge. Okay, it is PP delocalization, PP delocalization. Okay, PP delocalization. Okay. Secondly, allyl and benzyl cations have comparable stability that of secondary alkyl carpetine, that of secondary alkyl carbocation, even though both are primary carbocations. Both allyl and benzyl are 1 degree carbocations. Okay, so there are many books they show that tertiary carbocation is more stable than benzyl carbocation, which is more stable than allyl carbocation, as allyl carbocation shows only 2 resonating structures and benzyl shows 4 resonating structures, which is approximately to secondary alkyl carbocation, which is more stable than primary carbocation and which is more stable than vinyl carbocation. Vinyl carbocation is less stable. Okay. which is further more stable than methyl carpetine. This is the order. Okay. In case of vinyl carpetine, the stability is less because the positive charge is on more electronegative sp hybridized carbon. And as the rule says, that a more electronegative element or atom should not have the positive charge. Positive charge is on more electronegative sp hybridized carbon. Understood? Okay. Next, the order of stability among tertiary, secondary, and primary allylic carpetine. Follow the order. Tertiary is more stable than secondary, which is further more stable than primary. Next, same order is followed by benzylic carpetine, followed by benzylic carpetine. Okay. Now, there is a very important and unique order. Tropyliumine This is tropylium ion, which is actual a secondary carpetine, is more stable than triphenyl carpetine, which is more stable than diphenyl carpetine, which is more stable than trialkyl carpetine, which is more stable than benzyl carpetine. So please remember this order. As previously we have discussed that benzyl carpetine is more stable than trialkyl carpetine, but there are many researchers, there are many books which says that trialkyl carpetine is more stable than benzyl cation because benzyl cation is primary. Okay, so we cannot compare the stability of primary and tertiary actually. Comparatively, benzyl carpetine is equivalent or more stable than secondary. Okay, so it is 1 degree. Okay, benzyl carpetine. It is tertiary. Okay, this is also secondary. This is tertiary. Okay, it shows this much amount of stabilization because of aromatic stabilization. Aromatic stabilization. Okay. Now we are going to discuss about the stability of carbanions explained by resonance. Okay. Stability of carbanion. Okay. Now, more will be the resonance, more will be the stability of carbanion. More will be the stability of carbanion. Like for first example, allylic carbanion is the first, vinylic carbanion second, and ethyl carbanion, that is primary carbanion, third. Now, which is more stable? So here you can see conjugation is there. So first is more stable. Okay. Then comes the second, because negative charge is on more electronegative sp hybridized carbon. Second is more stabilized, and the third last. Okay. Second order. In case of alcohols, here the maximum negative inductive effect can be seen of OH. Here the minimum, because distance is more, OH. So this is more stable than this, which is in turn more stable than this. Third, nitro, methyl carb anion, distance is increased. Here the electron releasing group is there, so it will decrease the stability. Okay, but the NO2 is attached to the more electronegative, means the carbon having a negative charge, so NO2 will withdraw. So NO2 will nullify the effect of methyl group. Here NO2 is placed farther distance away from this carbonyl. So the overall order is first, then third, and then second. This is first, this is second, and this is third. Understood? More will be the pi bond, more will be the resonance. Here you can see this is first, this is second, and here it is third. So here you can see the charge is localized. It will not move. Okay. So the stability will be second, then first, then third. Because charge is localized here. Okay. Then tritial, that is triphenyl. minus is more stable than diphenyl minus. Okay, because more number of the phenyl groups, more will be the electron withdrawing nature we can see. Benzyl carbanion is also stabilized by the resonance. Understood? Negative resonating group minus R group increases the stability, while plus R group decreases the stability. Okay, like for example, so you can see the bond will shift here, positive charge here, okay, minus, lone pair will make a bond here, this bond will shift here. Okay, so minus R group, then this, and then the plus R. OCH3. Okay, understood? Stability of ethanide ethanidine, and ethynidine. Minus this carbon is least electronegative at is sp3 hybridized. This carbon is sp2 hybridized, somewhat more electronegative, and this is most stable because this is sp hybridized. Understood? These are the relative orders. Now comes the stability of free radicals. Same here, more resonance, more will be the stability. Like here to no resonance, more resonance, less resonance. So third, then first, then second. Triphenyl, diphenyl, benzyl, allyl, tertiary alkyl, secondary alkyl, primary alkyl, and then methyl. This is the relative order of stability of free radicals. Okay, free radicals, as you know, they are the odd electron species. Okay, now comes the application of resonance. Okay, we have completed the application of resonance. Okay, but now we are going to discuss about the application of resonance in explaining the acidic strength. For an acid, this is a hypothetical acid. You can see the existence of an equilibrium or a state of equilibrium. So according to the law of mass action, the dissociation constant Ka will be the product molar concentrations upon reactant. Okay, where K is the dissociation constant. Now, if Ka is more will be the acidic strength, because more will be the ionization, more will be the product. And if we take the negative logarithm of K, that is pKa, is inversely proportional to log of K. So if pKa is high, then it simply means that the acid is weak. The stability of an conjugate base defines the acidic strength. Acidic strength is directly proportional to stability of conjugate base. Which is directly proportional to negative mesomeric effect, electron withdrawing, and inversely proportional to positive mesomeric effect, electron releasing. Negative inductive effect, okay? Like when we compare acidity of phenols and alcohols, now in case of phenol, a more stabilized phenoxide ion is prepared, which is resonance stabilized. Okay, while in case of alkoxide ion, there is no resonance. no resonance. Okay, that is why the conjugate base of phenol is more stable than alcohol, and that is why phenols are more acidic than alcohols. Alcohols, they are even weaker acids than water. Okay, now if we compare the acidity of substituted phenols, if the stability of phenoxide ion increases, then more will be the acidic character. If the stability of phenoxide ion decreases, lesser will be the acidic character. Okay, less acidic. Understood? Like minus R groups, minus I groups increases the stability of phenoxide. Like if we compare the ortho substituted product, in case of ortho nitrophenol, you can see nitrogen is more electronegative, oxygen is much more electronegative than nitrogen. So this oxygen of NO2 makes a hydrogen bond with H, and that is why the ionization of H into H plus, it decreases. Okay, it is in comparison to the paranitrophenol. Okay, so here basically minus R effect is suppressed by minus I effect. In orthonitrophenol, because of intramolecular hydrogen bonding, the tendency to release H plus decreases. Okay, minus I power is maximum at ortho position because it is a distant effect when based on the distance inductive effect is measured. Okay, if the compound is meta, then both minus I and minus R. But the fact is, at meta position there is no resonance, no resonance. There is only minus I. No resonance at meta, only minus I. While in case of para, it is stabilized by both minus R and minus I, in which minus I is less as the NO2 group is situated at the maximum distance. Okay. So if we compare the stability order, this is minus I gets suppressed and minus R dominates. Understood? Based on all the factors, including hydrogen bonding, the order is para-nitrophenol is most acidic, then ortho, which in turn more acidic than meta, which in turn more acidic than phenol. Okay? Now, acidity of substituted benzoic acids. Always remember there is a ortho effect, that ortho substituted benzoic acids are always stronger than meta and para. Then meta and para. It is known as what? Ortho effect. Okay. Now, wait a minute. Yeah. So we were discussing about the ortho effect. So ortho effect says at the ortho position, whether it is an electron withdrawing group like NO2, okay, or whether it is an electron releasing group, okay, ortho acids are always stronger than para and meta isomers. Okay. In case of ortho substituted carboxylic acids, the effect is done both by minus R and minus I, but minus I being more in power, or we can say maximum effect is done by negative inductive effect. Okay, so according to ortho effect, the ortho substituted benzoic acids, whether the substituent is electron withdrawing or releasing, substituent is electron withdrawing or electron releasing. Okay, orthoisomers are stronger acids than meta and para. Okay, ortho effect basically includes intramolecular hydrogen bonding plus steric inhibition of resonance or protonation inhibition. Okay, groups like OH, Cl, NO2 will cause more stabilization of carboxylate ion due to direct interaction through intramolecular hydrogen bonding. Due to direct interaction through H bonding. Understood? Now, always remember electron withdrawing groups increases the stability of carboxylate anion, thus increases the acidic character. Thus increases the acidic character. Okay. As the number of electron withdrawing groups attached at a particular position increases, the acidic character also increases. Okay. On increasing the power of electron withdrawing group, the acidic character increases. Okay, so this is the glimpse regarding the acidic character of carboxylic acids. Okay, now when we compare acidic character of carboxylic acids and alcohols, carboxylic acid shows, means the resonance hybrid of carboxylic acids, they show equivalent resonating structures. That is why they are more acidic than alcohols. Okay. Last is electron releasing group decreases the acidic character of carboxylic acids. Okay. So my dear students, this is about the acidic character of carboxylic acids. Okay. Now we are going to discuss about the basic character. As we discussed that acidic strength depends upon the stabilization of conjugate base, there are certain reasons to explain the basic character of compounds as well. Okay, on the basis of resonance. On the basis of resonance. Okay. For example, on comparing the basic strength of ammonia and aniline. Ammonia is NH3. You can see the lone pair is readily available for protonation. Okay, for protonation. When ammonia, the lone pair, can be easily available to any H plus, so H plus attack is very fast. But in case of aromatic amines like aniline, the lone pair is involved in resonance. As the lone pair is involved in resonance, it won't be freely available for protonation, and that is why the basic character decreases. Basic nature of aromatic amines is less than ammonia. Okay, is that understood? The basic character of aromatic amines is less than ammonia. The main reason is that in case of ammonia, the lone pair is freely available, but in case of aromatic amines like aniline, the availability of lone pair it get decreased. Understood? Because the lone pair is involved in resonance. For bases, if the value of Kb is high, the basic strength increases. Okay? If the value of pKb is 1 upon log Kb, so everything stays same as we have discussed in for acids. This is aniline. This is benzylamine. So benzylamine is more basic than aniline. Effect of cross conjugation on basicity. For example, if we talk about amides, the basic character of amide is lesser in comparison to amines. Their reason is resonance. Okay. So due to delocalization and minus I effect of carbonyl group, amides are less basic than amines. Okay. But in case of benzamide, due to cross conjugation, basic character increases. The basic character increases. Okay? The reason is that pi bond of C double bond O is in conjugation with benzene ring as well as lone pair of nitrogen. So my dear students, this is about the basic character of amines. Okay, explain on the basis of resonance how resonance can be an explanatory and it can provide an explanatory detail. Okay, to study the basic character of amines. Okay, we are left over with the electromeric effect, hyperconjugation, and the reagents like nucleophiles, electrophiles, okay, and types of reactions. So we will be doing the types of reactions in the coming lectures. Till then, bye bye everyone. Take care, stay safe, stay healthy.